All right, so let's talk about Sir Isaac Newton. You definitely learned his three laws of motion back in school, right? But what if I told you that our gut feeling, our everyday intuition, is actually pretty terrible at understanding them? Yeah, let's pull back the curtain on the physics that's secretly running pretty much everything.
So, let's start with a little thought experiment. Just picture an object that's perfectly still. Maybe it's a coffee mug on your desk, or a parked car. It's not moving at all. So, are there any forces acting on it? Your first thought might be, well, no, of course not. It's just sitting there. But is it really that simple?
Okay, now look at this. We've got a cube just floating in midair, perfectly still. No strings, no hidden platforms. It seems like the very definition of being force-free. But as you're about to see, what's really happening is way, way cooler.
To crack that little puzzle, we have to start with Newton's first law. And here's the secret. It's not about having no forces at all. It's all about resisting change.
You know, this right here is probably the biggest mix-up. We feel like if you want to keep something moving, you got to keep pushing it, right? But Newton's law says the complete opposite. An object in motion is totally happy to just keep on moving, forever, unless some unbalanced force, like friction or air resistance, gets in the way. And this whole tendency has a name: inertia. Honestly, you can just think of it as the universe's built-in laziness. Step that's sitting still wants to keep sitting still, and step that's moving wants to keep on moving. Which brings us right back to our floating cube. See, it isn't force-free at all. It's actually caught in a perfect cosmic tug of war. You've got gravity pulling it down and a magnetic field pushing it up with the exact same amount of oomph. The forces are completely balanced. And since there's no net force pushing it one way or the other, its state of motion, which is being perfectly still, just doesn't change. And this is the other half of that same law. Imagine a rocket way out in deep space between galaxies. The moment it cuts its engines, that's it. There's nothing out there to slow it down. No air, barely any gravity, so it'll just coast in a perfectly straight line at the same speed, maybe for billions of years. It just keeps doing what it's doing. Okay, so Law 1 tells us that if you have an unbalanced force, you're going to change an object's motion, which of course leads to the next big question that Law 2 answers. Change it by how much, right? This is where we get to the numbers.
F equals ma. It might just be the most famous equation in all of physics. And these three little letters, they completely changed how we think about the link between force and motion.
So what does it really mean?
Well, it's saying that an object's acceleration, how quickly it speeds up, slows down, or changes direction, depends on just two things. The more force you use, the more it accelerates. But the more mass it has, the less it accelerates.
Think about it this way. If you have the exact same engine, and you put it in a tiny little sports car, and then in a giant semi-truck, which one is going to win a race? The car, obviously. Same force but way less mass means way more acceleration. You have absolutely felt this law in action every time you go to the grocery store. Pushing an empty shopping cart? Easy. But once you load it up, it's got way more mass. Now you have to push a lot harder just to get it moving at the same speed. Same push, different mass, different acceleration. A rocket launch is such a cool example of F equals m, because the mass is constantly changing. At liftoff, the rocket is unbelievably heavy with all that fuel, so it kind of struggles to get going, accelerating slowly. But as it burns through thousands of pounds of fuel every second, its mass goes down. The engines are still pushing with the same constant force, but they're pushing a much lighter object. So what happens? Its acceleration goes through the roof, and it just gets faster and faster and faster. All right, on to the third and final law. Now, this one can be the trickiest to wrap your head around, but it describes something fundamental that happens in every single interaction in the entire universe. I like to call it the cosmic pushback. You've all heard the famous phrase, straight from Newton himself, for every action, there is an equal and opposite reaction. Sounds simple enough, right? But it also creates a really confusing question. I mean, think about it. If every time you push on something, it pushes back with the exact same force, shouldn't everything just cancel out? How can anything ever actually start moving? It's a fantastic question, and luckily the answer is beautifully simple. Here's the secret. The action and reaction forces are always acting on different objects. Let's take a swimming fish. Its fin pushes the water backward. That's the action. And in reaction, the water pushes the fish forward.
The forces don't cancel each other out because one force is on the water and the other is on the fish. And the fish moves because of the force that's acting on it. Simple as that.
So there you have it, 3 laws. They might seem kind of simple when you break them down, but what they describe is just enormous. These laws govern how things move on literally every scale you can imagine, from a ball rolling in your backyard to the slow dance of galaxies.
Just think about sports. Newton's second law, F equals ma, is the playbook. A baseball player knows, intuitively or not, that if they swing the bat with double the force, the ball is going to accelerate at double the rate. It's predictable, it's powerful.
Now let's zoom all the way out. Look at these 2 galaxies, pulling on each other with the force of gravity over millions of years. This is Newton's third law playing out on a truly cosmic stage. Each galaxy is pulling on the other with an equal and opposite force, a cosmic waltz governed by the exact same rules that let a fish swim through the water. It's incredible.
I mean, the legacy of these 3 little laws is just stunning. Think about it for a second. They were published way back in 1687. And yet those same rules allowed us to calculate everything needed for the 6.2 million pound Saturn V rocket to land on the moon in 1969. And this isn't just ancient history. Today, engineers rely on these laws every single day to design safer cars, to build stronger bridges, and to chart the course for the probes we send out to explore the cosmos.
So, what's the big takeaway here? Newton basically gave us the official rulebook from motion. His laws tell us how things move with an accuracy that is just mind-blowing. But they leave us with an even deeper mystery. They don't tell us why forces like gravity exist in the first place or what they fundamentally are. So what is this invisible fabric of pushes and pulls that holds the entire universe together? Well, that's a question for another day.